next one is called multiplication by an exponential sequence. By an exponential sequence. You have x of n that is being multiplied by z0 power n. That is the exponential sequence. Okay, so let us see what are the implications and how does this give us some new insights. So we have property number 3, multiplication by an exponential sequence. Multiplication by exponential sequence. So we are given that x of n has got a z transform given by x of z. We want to know what is the z transform of z0 power n x of n. What is the corresponding z transform? So we will write this as summation n equal to minus infinity to infinity z0 power n x of n. Okay, it is just a mathematical substitution, but it gives you tremendous amount of insight. Z power minus n. Okay, now I am going to write it in a form which should be very interesting, and so pay close attention to it. N equal to minus infinity to infinity x of n z by z0 raised to the power minus n. Okay, z by z0 raised to the power n. Okay, now supposing the original sequence had an ROC given by mod z greater than RR less than RL. Let us say it is a two-sided sequence, it has got two limits, limit for the right-sided sequence and also a limit for the left-sided sequence. Okay. Now what we find is that z in the original expression has been replaced by z by z0. So the ROC for this sequence, ROC for this particular transform will be mod z by z0, okay, and it will be greater than RR less than RL. So what we have done is this exponential scaling, we have taken it as a scaling of the z variable. So mod z by z0, mod z was previously between the limits RR and RL. Now because of the scaling of z0, mod z by z0 together, this is between RR and RL. Now this can be written as mod z greater than z0 mod z0 RR less than mod z0 RL. This is actually a very, very powerful, powerful result, because what it is saying is that by applying an exponential sequence, this is like saying I am going to scale the ROC. Scale the ROC. If mod z0 is greater than 1, then you are expanding the ROC. Remember, you are expanding the ROC. Expanding the ROC. And mod z less than 1 will give you a shrinking of the ROC. Less than 1 will give you a shrinking of the ROC. Shrinking of the ROC. Okay, so basically this is a way by which we can expand or shrink the ROC, and this is a very, very powerful result which is there for the Z transform. Okay, and so this is something that we always want to keep in mind, that the Z transform has this unique property that you can apply a sort of scaling by doing an exponential multiplication in the time domain. And we will find that there are many cases where this will come out to be an important result. So this multiplication by an exponential sequence can be, one of it you can of course look at it in the following way. So let us take the case where Z0 is of the form e power j omega naught. It's a complex exponential. It's not a r e power j. So if you take this as a, then we know that e power j omega naught n x of n, we know that in terms of DTFT this will give us x e of j omega minus omega naught, right? This is a important expression. Now the same thing if you write down for x of z is equal to summation n equal to minus infinity to infinity e power j omega naught n x of n, that's the sequence that we are for which you are computing the z transform, z power minus n. This can be written as summation n equal to minus infinity to infinity x of n z e power minus j omega naught raised to the power minus n. Okay, so this is the same expression as x of z, but z has been replaced with z e power minus j omega naught, e power minus j omega naught. Okay, and now if you were to look at it on the unit circle, that means z is equal to e power j omega, what you will get is e power j omega minus omega naught, which will be the same as the original DTFT property. Okay, so if you multiply by e power j omega naught n x of n, the corresponding z transform is x of z e power minus j omega naught. Okay, on the unit circle it will be a shift by omega naught, but at other points you have to write it as z e power minus j omega naught. Okay, so this is case 1. So this is case 1. You've taken this in this form. Case 2. Z naught equal to R naught, some real constant, real valued. Okay, so in this case we have R naught raised to the power n x of n. This is going to give me x of z by R naught. Just go ahead and substitute, you will get this as the expression. Okay, and this is going to affect your ROC. ROC is going to be mod z if depending upon the limits. Let me just write this in the following way, mod z greater than R naught times RR less than R naught times RL. So basically it's going to result in a scaling of this function. Okay, case 3, very important. Case 3, z is equal to the most general form. It's not only r, not only omega naught. It is r naught e power j omega naught n. Okay, so what you find here is a combination of scaling of z, which will be introduced by r naught. Combination of scaling of z, scaling of the ROC because of R naught, and there will also scaling of the ROC, and there will also be a frequency shift because of the e power j omega naught n, frequency shift. Okay, so let us see if we can apply this in a very simple practical example. Supposing I have a sequence which is given by x of z equal to 1 over 1 minus 1.1 z inverse. Okay, so you know that this corresponds to 1 plus 1.1 z inverse plus 1.1 whole squared z power minus 2 and so on, and this will have a condition that mod z is greater than 1.1. Okay, so the ROC does not include the unit circle. ROC does not include the unit circle. Okay, If ROC does not include the unit circle, then that means the DTFT does not exist. It's not an absolutely summable sequence. All right. Now, what we are going to look at is the following sequence. Okay, we're going to look at Z0 power n x of n, where Z0 equal to 1 over 1.2. Okay, so basically it's the form of a scaling factor. Okay, so now if you compute x of z, this will be equal to 1 plus 1.1 divided by 1.2 z inverse, 1.1 divided by 1.2 whole squared z power minus 2 and so on. Okay, so basically what we are doing is we are applying the multiplicative or the exponential scaling z0 power n, and so this is the expression. So this can be written as 1 over 1 minus 1.1 by 1.2 z inverse, 1.2 z inverse. Okay, let me call this as some value beta. So ROC is mod z greater than beta. And what is beta? Beta is equal to 1.1 by 1.2. So which means that this unit circle now is included in the region of convergence. This ROC includes the unit circle. So which means that the Fourier transform also will exist. So this is a way of saying that we can write the expression. So this we can write this is actually x1 of z. This is a modified sequence. This is the same as x of z by z0. Okay, this is the same as x of 1.2 z. Okay, this is the expression that we have. This is the effect of scaling the or multiplying by an exponential sequence. So what we find is that by introducing the correct exponential sequence, you can then get a condition where you can analyze not only the Z transform, you can also analyze the DTFT if you need. So basically this is a way by which we can exploit the properties. Okay, so let us look one more time. We have looked at the expression of the Z0 power n x of n gives you x of z by z0. Remember, this is what we showed, and the corresponding whatever is the right-sided limit, that will be multiplied by mod z0. Left side will be multiplied. So rather than write it like this, I prefer to write it in the following form: mod z greater than mod z0 times rr. Okay, that's the this limit. Then mod z0 times RL, that's going to be the right-sided limit. So both of these are the limits that we have. Now the property number 4 I'm going to tick because we have already derived the differentiation property. So this is the property of differentiation. Differentiating in the time domain. Now comes a set of transform relationships which will involve conjugation. Okay. Now, unlike the DTFT, the conjugation requires us to pay very careful attention to how we are going to do the conjugation. So let me just introduce the notion of conjugation, and then at that point we will stop and pick it up in the next session. Okay, so I'm just going to introduce the notions of conjugation, so that you are aware of what exactly the conjugation involves, and we can then study this in detail next time. X of z equal to summation n equal to minus infinity to infinity x of n z raised to the power minus n. Okay. Now if I conjugate x of z, That means I have conjugated the term on the left hand side. That means I must conjugate the term on the terms on my right hand side. So this will be summation n equal to minus infinity to infinity x of n z raised to the power minus n the whole conjugate. Everything within the sum within the bracket must be conjugated. So this will be equal to summation n equal to minus infinity to infinity x conjugate of n. X of n could be a complex sequence, so x of n has to be conjugated. Is z a complex number? Yes. So z also has to be conjugated. Z power minus n conjugate. Okay. So very, very important on how we go ahead and simplify this. A few things to note. Z power minus n conjugate the same as z conjugate raised to the power minus n. And that's how did I say that? This is the z power minus n conjugate. This is the same as 1 by z raised to the power n conjugate. And so basically, you can do the conjugation, and then so this is the same as 1 by z conjugate raised to the power n, the same as z conjugate raised to the power minus n. Okay, so there are some simple relationships which we must look at carefully. Anytime you have a doubt, what the best thing is to say z is equal to r e of j omega. Okay, we have this as a basic relationship. Okay, z power minus n, what will that give me? R power minus n e power minus j omega n. Z power minus n conjugate, what will that give me? It will give me r power minus n e power j omega n. Are you following that? Okay. Now similarly, what if you take z conjugate? Z conjugate is r e power minus j omega. Z conjugate raised to the power n, raised to the power minus n. This will be r raised to the power minus n e power j omega n. So basically you can anytime you have a doubt on how these things relate, conjugation inside, outside, raised to the power n, you can always go back to first principles, substitute and get the corresponding relationships. Okay. So what we are going to do in the next session is to work with various aspects of conjugation and the properties that it brings together. So this will help us understand how to represent the ROC, not only get the Z transform, but also get the region of convergence for when you conjugate a sequence. And what is the corresponding ROC, what is the corresponding Z transform. And so the conjugation is an important concept. I would like to treat it as a separate unit of study, and that we will do in the next session. So we will pick it up from here. I hope you will have a chance to review this material, look at some worked examples, look at some discussion points in the practice assignments, and then we will pick it up from there in the next session. Thank you.